Hello everybody to our statistics course. We started last week just with an overview about the content, and yeah, then we started with a revision, and with this we want to go on. First, we all remembered what is a random variable, how to more or less in a simple example we calculate probabilities, we calculate an expectation value, we distinguished between discrete and continuous variables. In general, we remembered what is a cumulative distribution function, expected value, and variance in general, some rules of calculation for variance and value of expectation. Yeah, and then we want to start with the main descriptive parameters we are calculating. In statistics, I think all these numbers you already know, and maybe two new one I will introduce for you. This is the so-called skewness and kurtosis. Yeah, then please remember what is the median. So if we have some data set, let's say 70 or better 71 data points, and what is then the median? The median is then defined, so to speak, as the middle of your distribution. So if you have the data, then we put it in a row from the lowest to the highest, and if we have 71 data points, then it would mean that the 36th data point in a row would be our median. So the median just splits our distribution in two halves, and on both sides we have 50% of our data, and then it is defined that if you have an even number of data points, because this means there is no data point in between, then we define it as the arithmetic mean of the two data points in the middle. Yeah, and before I go on, that we do not only talk about these numbers in an abstract way, let's take some distribution, and for this we take just the height of ourselves. So if I'm number 1, then I'm 178 centimeters. So maybe I can ask you, what is your height? You can just type it in the chat, or if you want, you can directly say me, what is your height? Do you know? 87, okay. And the other guys in the internet? 172, okay. What else? 190, 185, 190, 175, and 178, I think here. So it's 2 times 175? No. 72, 90, 75, 78, 175, and 178 again. Okay, a bit more to the right. Then 2 equal this plus 1. Faster. Yeah, and if you should calculate the median of this distribution, what would you do then? Idea? Now we should do it. Yeah. Okay, so we do this here. This is a good idea. And of course, we use our software package and here to sort, or what you also can, yeah, let's take sort here and due to height, and yeah, let's take the lowest one at first and then the highest one. Okay, and here we are. Well, these numbers, because there I had a formula, they now changed, but it is not that important. Or it is important because we have to know how many we have. Equals 1 plus this one. So, and now what we are doing? You can also participate in the internet. Well, actually, since our data set has an amount only of 7 data points, we just can directly look at this table and we see what is the median. So, yeah, it is number 4, yes, but what is the median of the distribution? This is the question. This is not number 4, but 178. So this is the median of the distribution. So let's put it, we will have some more numbers. Median is equals this one in the middle. So 3 points are lower or equal, because here by accident it happens that we have 2 data points with 178, but this doesn't matter. It could also be that every data point is 178 and then also the median would be 178. And we have 3 numbers higher, so the fourth number is just in, in the middle. And I think we can also do it with median of this distribution. Fortunately, we have the same point. Okay, done. The next one, arithmetic mean. Arithmetic mean is just summing up all numbers you have and dividing by the amount of your data set. So then you can take your calculator and typing in 172 plus 175 and so on and so on. But I think it is also quite good that you just practice it, how to calculate it within some standard software like Excel. So the formula is just sum. these numbers, and then we divide 1265 by in order to get the arithmetic mean. What we have to do now. I know this is trivial, but I want that you are doing it. So, yeah, divided by 7. So, divided by, and then I also take this number, because the next time maybe I have 11 data points or something like else, and then I can directly copy my number. So this is then this number here, or of course there's also a formula for the arithmetic mean, and this in the German version is just Mittelwert or mean. So we take this one, brackets closing, and of course this is also the same one. Well, and if we are talking about what is the mean of a distribution, well, we do not think very much about it. Well, we more or less, if nothing else is said, we more or less directly anticipate that we mean the arithmetic mean. So summing up all numbers and dividing by the amount of our distribution. Why is it the case that the arithmetic mean has this really important? But why is this the really important number? Well, and for this, maybe from school, you know that if you look at a triangle, and if this triangle is not too flat, then what you can do then is you take always the half of one of your sides and putting a line to the corner, and then all these 3 lines are crossing in one point, and the nice property of this point where these 3 lines are crossing is that you can put the finger below your triangle, and then your triangle will lie on your finger, because this is just the center of gravity. Well, and the arithmetic mean is nothing else than to calculate this for a whole distribution and not only for 3 corners. And yeah, what we else have is that the arithmetic mean has the nice property that it is invariant via a linear transformation. Remember, also we have just these shift when we are calculating expected values. And for this, I think you have done in your introductory course also the arithmetic mean we quite often take as an estimator for an expected value. Well, and for this, they should have the same properties. And maybe the most important property of the arithmetic mean is then, and here we already have the square, so the variance is coming in, that the arithmetic mean has the property that if we take any mean we could think of our distribution, that if we calculate the sum of the squared distance of all our data points with respect to the arithmetic mean, then these aggregated distances, squared distances, with respect to the arithmetic mean is the lowest one compared to any other means you can think of. Because in a general way, the median is also a mean of your distribution. But if you calculate the squared distances with respect to the median, then in general, this would be larger than the sum of the squared distances relative to the arithmetic mean. Well, and for this, then, you see also that this is a quite nice property, because in general, what would you call a good estimator? Well, you want to describe your whole distribution, so I want to choose an estimator which represents my distribution, and then the fluctuation around these representer of my distribution. This should be as small as possible. So this we would call then a good property. Well, there is no reason that this should be then, of course, a reason that we always have to choose the arithmetic mean. But we want to describe with this number our distribution, and therefore we can think of what properties should my representator have, and this is some property which seems to be a nice property. Okay, but of course there are also other, where we are here, other means we could calculate, and the next one is the geometric mean. And what is the geometric mean? The geometric mean is now not summing all up, dividing by the amount of our of our data set, but multiplying every number and then taking the nth root of this number, and n is the amount of our data set. So let's then go here and calculate the geometric mean. And here, now we need the product. Also for this, we have a formula. So you need not to have to type 172 times 175 and so on. And then we take the nth root. So this one, this, oh, I put it here. So then this equals this to 1 over 7. And of course, for this we also have a formula, geometric mean of these numbers here. Oh, what's here? What's happening here? This one. Sorry. So Yeah, what we see here is that these numbers are quite close. Well, the reason for this is that we see here that these numbers are not really fluctuating. So we just in a maximum of around 10 centimeters relative to almost 200 centimeters in absolute value, and therefore these two means are not too far away from each other. But as I told you, you're studying economics, that quite often, if you are talking about growth rates, then the right thing to do in order to average growth rates, then you have to use the geometric mean and not the arithmetic mean. And the last mean, we have also the so-called harmonic mean. And here we are doing something quite funny. We are summing now all numbers, but not the numbers itself, but 1 over the numbers. And then we are dividing the amount of our of our sample by the sum. And in a minute I show you that it is not that far away from the geometric mean or the arithmetic mean and how you can see this. But let's calculate the arithmetic mean. So for the arithmetic mean, at first we have to calculate the inversion. So this one over this one. All these we have to sum up. Therefore, this we just can copy this formula here. And then we have to calculate 7 divided by these sum of the inverted numbers. And again, you see we have a number quite close to the geometric and the arithmetic mean. And then this would here the harmonic mean is this one. And of course, we have also the harmonic mean formula, and then we can directly calculate this one. Well, and if we look how we calculate these numbers, then let's take just x1 and x2, and we have the arithmetic mean. What we are doing then, this is 1/2 open brackets x1 plus x2. Geometric mean, what is it? Well, also x1, x2. We also take a 1/2, but I'm just writing it up here. Taking this and not taking a plus sign, but the multiplication sign. So we interchange only this sign, and the 1/2 goes up to an exponent. So it looks very similar. We have only other signs. And if we take the harmonic mean, well, in this case, we can say this is x1, x2, and also 1/2. again in brackets. And what we are now doing is just writing here up to -1, up to -1. We have to take the sum. Then it has to go in the denominator. So here a -1. And we have to take 2 divided by. So this gets also just a -1. So the harmonic mean is again more or less the same as the arithmetic mean, only putting at every number, at every part of our formula that you have to invert it. Exponent up to -1. Well, and sometimes it's you have, if you want to average something, then you have to take the harmonic mean. For example, driving with 100 kilometers per hour from Wilhelmshaven to Oldenburg. Let's say this is, I don't know, 50 kilometers or something like this. It's easy to calculate if we take 50 kilometers. And then driving back from Oldenburg to Wilhelmshaven with 50 kilometers per hour. What is the average velocity? Well, this we can do as an homework, but it is quite clear that the average velocity is, of course, not 75. Why is it not 75? If I'm driving a distance of 50 kilometers with 100 kilometers per hour, then I take less time if I'm driving back with only 50 kilometers. Because for the first part, I'm driving twice as fast. And for this, directly, I know that the average velocity has to be lower than 75 kilometers per hour. Well, try it at home, and well, then you will see that you have to take the average here with the harmonic mean. Okay, so these are 3 different means we quite often use. On our exercise sheet, I already uploaded there. I gave you also an example from economics where you have to use the harmonic mean. This we will do later on. Okay, so now we have a representative describing the whole distribution. And we already talked about the property of the arithmetic mean, that this is the number where the sum of the squared distances is the lowest we can achieve. So what we also quite often want to do is, well, I want to describe the fluctuation of my distribution. And for this, I also then calculate or I can think of how can I find good numbers to describe the dispersion of my distribution. Now, and the easiest one or the first one you can think of is I just have a look at my numbers and what is the maximum range my numbers are lying in. Well, and this is, of course, just called range. So let's calculate the range of our distribution. Well, and the range is just the difference between the largest and the smallest number I have. So let's take here the maximum and the minimum value. And for this, we have also a formula. Now I have 7 and I just have a look and I see in 172 and 190. Okay, but think of that you have 253 data points. Then you are looking with your finger. This takes some time, even, or think of a data set with 1,000 numbers. So max is just the maximum of your data set, and surprisingly, minimum is the minimum of your data set. So what we obtain then is max minus min. And what we also should do is to keep in mind, you could have also data points which have negative numbers. And for this, we should also take the absolute value of this number. This is, of course, also 18, but if it's negative, then you would take just the absolute value. So you would have always a plus sign. And yeah, this is also how you mostly do it. Well, if I remember it right, we have also range, or no, no, I do not remember what is the formula in Excel for this range. Maybe you can look it up. Okay, this would be then 18. Yeah, but what is the shortfall of this number? Well, it could also be that maybe here we would have some giant within our distribution. I think the longest guy who ever lived was some Ukrainian guy, and he was about 2 meters 70. So, and think we would have here a number of 270, and all other numbers are just around 180. And then you would say a good description of my distribution is that our range is 90. But then I have to admit that this would not be a good number because there's only one outlier who is shifting me this range number. Well, and for this, we just had another number, and this is the mean absolute deviation. And for this, we just calculate the difference between our data point and now the mean, and here we then insert the arithmetic mean. Okay, and let's calculate the mean. And for this, we calculate the absolute value of xi minus x bar. So equals absolute value of our number minus the arithmetic mean. This was this. And since we want to calculate every number relative to this, we have to fix this number. And this you can do by typing F4 or by hand you inserting in front of the letter and the number for your cell a $sign. Going down, then we have all relative distances to the arithmetic mean. Again, we need the summation, and this number we have to divide again by the amount of our sample. So this one divided by 7 would be 5.67, and hopefully mean average. Did I remember this one? No, I don't know. I have to look it up. But you will have also a formula here for this one. Okay, then variance. Variance is now defined as the squared sum of the squared distances divided by the amount of our sample. So then let's go. Xi minus x bar squared equals, open this one, minus arithmetic mean fixed brackets squared sum and divided by 7. Biased variance, variance. So this is here's something wrong, I think, or this is too low. Oh yeah, because he just switched to the 190 here when I copied my formula. And this is also why I'm doing this with you. Because if you are doing statistics and having a look at your data, you always have to know what you are doing. And only feeding in your data, pressing enter, and then there come some numbers outside there, and you do not know what are these numbers about. Or at first, please just have a look at your data set. And if you have some routine, then you also already know, well, if I'm doing now statistics, the numbers who are coming out, the just descriptive numbers who are coming out, they should be in around this range or so. And if you then have a look at your output, then you should directly really wonder, well, here I calculated the mean average distance about 6, and now the variance where I calculate the square distances divided by 7 is a lower number this could not be right. So this is not B10, but A10. Oop. And then we hear this looks more reasonable that this is the variance. Okay. So then we have this one, and this is then, and here I think P is the right one. Let's see. Otherwise it's S. No, it's P. Because the variance with S is now the non-biased variance. And the non-biased variance is the same as the variance squared distance, but now not divided by n, but divided by n minus 1. So 267 divided by 7 minus 1. And since we have a very low number, our sample size is only 7 numbers, then you have really a large difference, because dividing by 7 or 6, then the number really differs. If you have a data set of 1,000 data points, then you yeah, not really bother which kind of variance you are calculating, because dividing your squared distances by 1,000 or by 1,001, then I think in the fourth digit or so, there's a difference. Okay, so 44. And here now the variance with S, and hopefully this works out. Yep. So, and why do we call this biased and this unbiased? Well, the reason is what we want to do. We have asked 100 people downtown Wilhelmshaven, do you like this product or not? Or how much you want to spend on this product in order to get a number out of your questionnaire. And yeah, what you want to do, you don't want to get only the information of these 100 people. Then you would say, well, I ask 100 people, so I assume roughly on average all people in Wilhelmshaven will spend for this product, I don't know, 25 euros. And then you also want to know the fluctuation. And for this, you want to have an estimator who, on average, is equal to your expected value. But since you do not know the whole distribution, you haven't asked 80,000 people, you have no information about this. But then you can theoretically show that the expected value of these unbiased variance divided by n minus 1 equals your true variance. And this is the true variance. And here, the expected value of sigma squared tilde is definitely not equaling your true variance. And this is the reason because why you are dividing by 1 over 1 minus 1 and n minus 1. Maybe if we have time, we I show you why this is the reason. But actually, you should know that this is the reason. And this is again what I'm talking about. You should, if you are doing statistics, you should know what you are doing. One anecdote, last week I was at a conference and there was some panel research. And then there was a talk about this panel research. And then was descriptive analysis, everything was okay. But the data which was represented, this was not a random sample. So it was also some questionnaire and so on, but they pre-selected who we are asking. It was not randomly chosen. Well, and then the talk was going on, and then it was explained, well, now we can talk about, this is our data set, and now we can make our conclusion to the whole distribution. And this you cannot do. If you do not have a randomly chosen data set, this is just not allowed. It is not possible. Well, then, and in the end, in the discussion, there was one guy. He was really friendly. He said, well, you can, everything what you are doing is everything is all right. You can make descriptive statistics, but you cannot conclude anything to the whole distribution. You cannot make any hypothesis testing. You cannot do any calculating any significance values and so on. And he was totally right saying this. Because there was a guy who was not knowing what he is doing. And this is quite often the case in statistics. And we will do here when I'm showing you the multilinear linear regression, then we will do also hypothesis testing. But then we have also always keep in mind, well, my data is a random sample. If this is not the case, then you cannot go further than purely descriptive statistics. And therefore, I also want you to know why are these numbers looking how they look. And not only sometimes in statistics courses, yeah, well, everybody is doing it like this. Okay, so then one property of the squared distances is that if we take our data set of our heights here, then this is centimeter. So this is centimeter. All this is centimeter. This is also centimeter. What is the unit of our variances? Square distances. So square distances, unit is not centimeter, but centimeter squared. Well, and now, again, what is the use of calculating these numbers? I want to describe my distribution. Describing my distribution means I have an average, maybe the arithmetic mean, and then I want to have a number describing the dispersion around it. Yeah, well, for practical issues, I just want to say, well, it's around it's 180 centimeters plus minus 5 or what. So with the absolute distance, I can say this 180 plus minus 5.7 centimeters. But what is the meaning? 180 plus minus 38 centimeters squared. So, and in order to come back to my unit of centimeters, surprisingly, I'm just taking the root. Then I'm back from squaring, and again I have my unit of centimeters. So standard deviation from the biased one, this would be then the root of biased, and the standard deviation of non-biased is then the root of the non-biased. And here, standard n is then hopefully the same number, and standard s is also the same number. Yeah, and now we can say, if we want for the dispersion, description of the dispersion, we can say 180 plus minus 6.2 or 6.7 if I choose the biased or unbiased variance. Yeah, and what else? Before we come to the third and fourth moment, if we have now we have the dispersion described by the standard deviation. And what else? What we are quite often do is then we want to compare the dispersion of, let's say, one experiment here, choosing the height of some guys. There we find 100 plus minus 6. And in another distribution, economics, spending money on some product, we get some numbers in euros. And then you get maybe 24 euros plus minus 4 euros. And then we want to compare maybe these two samples and want to say what sample has the higher fluctuation. But if you there have also different units, then it's quite hard to say which distribution has the larger dispersion. Because also think of, we can just rescale the height, not measuring in centimeters, but in millimeters. Then the absolute value of the dispersion is much larger. Or calculating or taking the other sample with euros, not in euros, but in cents. It's also times 100, the absolute number. And for this, we sometimes also calculate the coefficient of variation. And for this coefficient of variation, we just normalize our dispersion via our expected value or via our mean. Well, not the variance, but the standard deviation. Well, and then in our example, you have centimeters over centimeters, and this then the unit cancels out, and you have here now a number without a unit, and one can compare samples with different units. And this would be then the last one. Coefficient of variation. And yeah, here we also have to take biased and non-biased. And non-biased. So this would be then 6.1 divided by our arithmetic mean, and this 6.7 divided by our arithmetic mean. So, but now we have, I think in the first or second lecture, I told you already that, yeah, we could have a distribution which is looking more or less symmetrically, but we could have also a distribution which have some skewness on the left one or on the right side. And if we take only the variance or the mean absolute distance, then we have no information. Is there some long tail, and is there a part where we have much more probability mass? And in order to describe this, and just the question, have you dealt with skewness or kurtosis already in other courses, quantitative courses? Yep, might be. You have also already at least heard of it. Well, if we then look at it, well, because why we here calculating this relative in the skewness relative to the third exponent of standard deviation, or here also with the fourth one. This means that we always, yeah, want to somehow normalize these numbers, and then we can interpret these numbers. And this is also the reason where if you compare this again with the normal distribution, then we know that f of x is 2 pi sigma squared x minus mu over sigma squared. So here we have also the division through the standard deviation. And for this, in order to interpret skewness and kurtosis, we can then interpret these numbers relative to the normal distribution, and therefore they are defined in this way. Only that you know this. Okay, then let's calculate the kurtosis. So now it's the to the third exponent, not squared, the distances, divided, and here the unbiased or the biased standard. No, the unbiased. Which one do I take here? Biased, or I defined it with HUT. Where is it? Range. There, yeah, the unbiased one. So then let's go. This one. Now to the third, and for the kurtosis, I need it also to the fourth power. Third and fourth. And always the sum. And divided also by n. So equals this one divided by 7, and this one divided by 7, and then divided by the unbiased standard deviation to the third power and standard deviation to the fourth power. So this one divided by 6.7 to the third, and this one divided by 6.7 to the fourth. So then we have skewness equals this one, and kurtosis equals this one. Well, and if we have here the third power, then of course, if the number within the brackets is negative, raised by the power of 3, then the number is still negative. So the sum is then maybe the sum of plus and minus numbers, positive and negative numbers. So, and this means, of course, that the sum could be positive or could be negative. And for this, then, we have here, if we have a negative number or if we have a positive number, then we know that we have a left-tailed or a right-tailed distribution, just because of if this number is larger or lower than 0. Well, and we can also roughly interpret the amount. In our case, we have a quite small number, 0.11. Well, and this means that we quite close to a symmetric distribution. Well, we have only 7 data points. If we look at these numbers, then just the maximum and the minimum are roughly the same. Then we are here 175 and 185. So this is also quite the second largest are also and 187. They are also quite close in the same range relative to the arithmetic mean of our distribution. So we are not really surprised if we look at the data that our skewness has some shift to the left or to the right, but that we are quite close to 0. This is also not very surprisingly. Okay, and then in order to interpret the kurtosis, there we can show that the standard normal distribution. So what is the standard normal distribution? When we have an expected value of 0 and a standard deviation of 1. So this is n 0, 1. This is mu and sigma. And if we calculate the kurtosis of this standard normal distribution, then the kurtosis would be 3. Sometimes you find in other books about statistics that you also then define not that as the kurtosis, but this divided by 3 as the kurtosis in order to have a reference point of 1. But I think quite often, or in more cases, it is defined like this. And then, well, you have to keep in mind and you have to know that your reference point is now 3 if you want to interpret it relative to the normal distribution. Well, and if you have kurtosis larger than the kurtosis of the normal distribution, well, maybe then you could say I have here very long tails on the right and on the left side. Or in the other way, then my distribution is a bit narrower. But also in the exercises, I gave you examples that you have to be careful with this interpretation, because there are also some distributions, and this is then the case when your data is not situated around the around your mean. So if you have maybe two areas on the left and on the right side of your mean, then you have to be careful when you are interpreting the kurtosis like this, but this is better done when I show you the example. But in general, you could say, well, in general, if you have very large data sets and quite often the probability mass is centered around the arithmetic mean, then you could say, well, larger than 3 means I have fat tails, and lower than 3 means a bit more centered around our average numbers. Okay, so then I'm more or less done with my review, and maybe these two are some new aspects. Well, skewness and kurtosis are quite often in finance data, because then you are more interested how is your data distributed, and you are especially interested in finance data about the property of maybe fat tails. Because if you're just asking somebody downtown how much money you are spending, then you are quite often, if the number of your data set is large enough, then you are always coming quite close to the normal distribution. Or a good approximation or a good hypothesis is that your distribution is normally distributed. But in finance, we found that unfortunately these outliers, macroeconomics, to have a financial crisis, and then just 10 years later we have a corona crisis, that these outliers are more often than you would expect them from the normal distribution. And therefore it is quite interesting to go further, not only describing your distributions in finance and economics via averaging and the variance. Because you see, well, if I look at historical data, normal distribution is not the best choice. Yeah. Then in the end, I don't know if you have talked about this in your introductory courses. If we take here the mean absolute deviation compared to standard deviation, and this was sigma 1 over minus 1. We don't care now about the difference between minus 1 and 1, but sum xi minus x bar squared, then we could wonder, well, this formula is much easier than this one. There at first squaring, then taking the root. And this is, I think, also the much more intuitive one, if you want to describe dispersion. Well, I take just the difference and sum all the differences up, and I take the absolute value, because I do not want that if I'm lower than the average and higher than the average, that this is outweighing. So I think if you just ask anybody who hasn't done any statistics before, what would be a reasonable number to describe my fluctuation about the average, I think they would answer this would be a good number, and not this one. But this, I think, also when you have described data, you very rarely do this. You mostly choose this one. Well, and we call it standard deviation. So there has to be some reason, because we say that this is our standard number and not this one. Have you talked about the reason why we're using this one and not this one? Or we take this one and not this one? Reasons for using standard deviation and not mean absolute distance. And this, I think, is also something. Well, everybody is doing it, and then it's right. If everybody is doing anything, then it's right, or what? Well, there should be some reasons why this is a good choice. Well, it's when I started to think about these things, I have to admit, I have also to look up and think about why we are doing this, because in my introductory course as well, I just learned calculate the variances, and that's it. Well, first of all, maybe a practical value. Because how does this function look like? If we plot it, this means if we have a positive number, it's just a straight line with slope 1. Okay. If we have negative numbers, then we just reverse it and say it's a positive number. And this means, well, it's just a line with slope -1. Well, and this function has one problem here in its minimum, because then it's just flipping. And this means there are no derivative. Or when you are going from the left side, you have derivative -1, f prime. So f prime of x is -1 from the left, and f prime of x minus is +1 from the right. Well, and if you have no derivatives, we are in economics, we always want to maximize or minimize some things. The property which we need is first derivative is 0. So for practical issues, here it is hard to theoretically maximize or minimize some things. And of course, shifting my portfolio, what I want to do, I want maybe minimize the fluctuation of my interest, what is paying, what is paid. And then I cannot do the analysis, or not in a theoretical way, I cannot do the analysis with this function. Well, and if I take f of x is x squared, squared distances, then I have these nice that f prime of x is 2x. And then I can set f prime equals 0, and I can calculate my optimum or my minimum or maximum. And what else? Well, standard normal distribution again. And again, remember the central limit theorem. No matter what distribution you have, if your sample is as large enough, then approximately you are going in the neighborhood of the normal distribution. Only if you're doing finance, because we are then, maybe we human beings always decide in other ways that we cannot describe this with a normal distribution. But if you take biological processes, physical processes, everything, then always you find the normal distribution. Well, and this normal distribution again is described with two parameters, x minus mu over sigma squared. And here you find these squared distance in the description of the normal distribution, though the distribution you mostly find in nature. And for this, from a maybe philosophical standpoint, it is then a good choice of using the squared distance as the standard parameter of fluctuation. Well, and who has more or less invented this? This is going back to Carl Friedrich Gauss in the 17th century. He was asked by his master, the guy in Brunswick, and he asked him, well, I want to know how large my country is. And then Mr. Gauss was traveling around here, and he even traveled here just to the coast. One point where he was measuring the distances was in Jever, and the other one was at the windmill in Farel. And well, when he was measuring, then always from one point, he was maybe from Farel, he was looking to Rüstringersiel because Wilhelmshaven doesn't exist at this time, and then he looked from Jever to Rüstersiel, and then these points didn't match because of measuring errors. And when he then thought about, well, what would be a good way to correct my data? And there he invented the idea of these square distances, and then we come to one of the main topics of this lecture, to linear regression. So there is no must that we have to do it, but there are good reasons to do it with the square distance. Okay, so maybe hopefully you get from this lecture also that you know what you are doing and not only do what everybody else is doing. So thank you very much for today. And I gave you an exercise sheet. So this we will do then next week, and then we start with linear regression. Thank you.